Hi, I'm Mason Vale from Boise State University, and in this video we're going to talk about the basic concepts and implementation of a node-based linked list. If you're familiar with array-based lists, you know that they had strengths and weaknesses. An array-based list has an advantage of fast lookups of elements by their index positions, but a weakness is that there's a big O of n shifting cost for any insertion or deletion in the list other than at the very end. So an alternative to try to avoid that shifting cost is to create a structure that more closely matches the very flexible mental model of the interface, where a list is simply the sequence of elements, and elements can be inserted or deleted without any need to shift anything. To provide the necessary structure for a chain of objects of any kind, we'll introduce a very simple object called a node. Each node contains a reference to an element of its chosen data type, plus at least one reference to another node in the structure to create that link between one object and the next object in the list. For a list, we need at least to know the beginning of the list. The list needs a reference to the very first node in the list, and from there it can follow the next node references in each node object to traverse the chain. By looking at the elements in each node, we can actually see the contents of the list. For a single linked list, a node only has a reference to its next node. So all traversal of the list must begin at the beginning and move toward the end. A double linked list adds a second node reference to the previous node in the chain, which allows for backward traversal as well. Here we see a model of a single linked node and a double linked node. In the single linked node, each object contains one reference to an element of the generic type T and one reference to another node of the exact same type as this node. For a double linked node, we still have one reference to the generic type T element. We have the node reference to the next node in the chain, but we also add a second reference to the previous node in the chain. In this slide, we're contrasting the user's abstract perspective of a list from the programmer's implementation perspective. Above the green line, we see that the user perceives a list simply as the sequence of elements. So this list contains 4 elements, A, B, C, and D, in that order. The user only expects to interact with this list through the abstract data types interface methods. Below the green line, we see the programmer's perspective. So the programmer sees the list as a sequence of chained nodes, where each node has a reference to the next node in the list, and each one of those nodes is holding a reference to its corresponding list element in the same position. So there's exactly one-to-one relationship between nodes and elements. In order to traverse this single linked list, the list must have a reference to the head node. It must know where the beginning of this list exists, so it can start somewhere. Now, for convenience, a typical implementation of a single linked list not only keeps track of the head node, but it also keeps track of the tail node, the last node in the sequence. And that's simply for convenience and for efficiency. Because many additions are made to lists at the end of the list, it's more convenient to start with a reference that directly jumps us to the end of the list, rather than needing to start at the beginning and walking through an unknown number of elements before we find the last node. So the tail is optional, but it's almost always included for efficiency. In addition to head and tail node references, a typical single linked list implementation will also keep track of an integer value for the current size of the list. Again, this is for efficiency's sake. You could start at the beginning of a list and count nodes until you reach the end, but it's more efficient to simply keep track of the number of nodes currently, to increment that number when a new element is added and decrement that number whenever an element is removed. At this point, we have enough information that we can start writing code for our single linked list. We'll begin by defining a node class, a single linked node class. Now, this class could be written as a standalone class, especially if I want to reuse it for other linked structures, perhaps a stack or a queue, or it could be written as a private inner class of the list. Either way would be completely acceptable. Once we have our node class written, we'll begin implementing the list interface in our indexed unordered single linked list class. We start out by declaring our instance variables. So we'll include a head node and a tail node. We'll also include an integer for size. We'll initialize our instance variables in a constructor, and then we'll identify some basic utility methods that would be good to implement right away. Because it's so simple, I've gone ahead and written out a complete minimal implementation of my node class, and I've written it as a standalone class. I only need 2 instance variables, so I have a private element reference of the generic type T, which makes this node configurable for any data type, can hold any kind of element. I also have a single link, a link to the next node in the linked list. So those are my 2 instance variables. I've provided one constructor that takes in an element, because I would never create a node if I didn't already have an element. I haven't initialized my next reference yet. It would be possible, and some people would probably like to have a second constructor that takes in both the element and the next node reference, if you knew that already. I don't tend to use that one, so I've left it out of my implementation. All that remains in this node class are getters and setters for element and the next references. So I have a get element and set element. The node can return the element that it's responsible for storing. I can also replace the element in a given node using the set element method. Get next returns a reference to the next node in the chain, and set next can update that next reference to point to something else. Now, one other method that would probably be useful to have, especially for debugging purposes, is a toString method that reflects the element that's stored in that node. So that's something that I would recommend for debugging purposes, is a toString method. For my list class itself, I've declared a class, given it the name IUSingledLinkList, and I have it implementing my list interface indexed unsorted list, and I've made the generic types match. Because I've signed the contract with the indexed unsorted list interface to provide all of those methods, I'm going to let my IDE generate the unimplemented method stubs. So these are all of the methods that are defined by my indexed unsorted list interface that I'm required to supply an implementation for it. But before I get to implementing methods, I need my instance variables. So the 3 instance variables that we identified were a node reference, a node of type T, as we declared before, for the head, and another for the tail. I also need a private integer to reflect the current size of my list, the number of elements in my list. So these are my 3 instance variables. And if I have instance variables, I need a constructor. So I'm declaring a constructor, IUSingleLinkList. I don't need any parameters, but I need to initialize head, tail, and size. Head and tail are both references to a node, and I only have nodes that go along with an element in my list. In the beginning, when I first construct a list, there are no nodes. Therefore, head and tail are both null. So I'll set head and tail equal to null. Currently, there are no nodes in my list because there are no elements in my list. And size in the beginning is 0. So head and tail are both null, size is 0. And this initializes my brand new empty list. Constructs new empty list. Now looking through all of these methods that are provided, I have my add methods, remove methods, get and set methods, indexOf, first, last, contains, is empty, size, and my iterator methods. So useful utility methods to get out of the way right away would be things like size, is empty, indexOf, contains, things that I might need to use in other methods. So these are relatively easy to write, and they're useful when writing other methods. So I would recommend tackling those first. Size may be the easiest one of all to write because we have a size variable that we're keeping track of to represent the current size of the list. Is empty is also very easy to write because I can ask this list if its size is 0. There are actually several ways I could write the isEmpty method. Maybe the easiest is checking to see if size is 0. That's a possibility. Alternatively, If I'm being an object-oriented purist, I might check to see if my size method is returning 0 instead of using my instance variable. I would also know that my list is empty if head is null, and technically I would know it's empty if tail is null. Really, any of these could be used for my isEmpty method, but size equaling 0 or head equaling null are probably the two that are used most often. The indexOf method is a good one for us to start with because it's going to teach us a little bit about how we navigate through a linked list. Let's start out by recognizing that the indexOf method, according to the indexed unsorted list interface, returns the index, the first index of where that element is found in the list, or a -1 if it can't find that element in the list. So let's create an integer for the index that we're going to return, and we'll set it equal to -1 until we find an element, something else to return. So in the end, we'll return the index. In between declaring the index to be -1 and returning it, we'll give it a chance to find the element. Now, navigating through a linked list requires us to walk through node references until we find a node that contains something we're looking for. So in order to traverse a linked list, I need some node reference to provide a cursor, if you will, or a movable reference. So I'm going to create this, I'll call it current. This is my current node, the one I'm looking at currently. And every node traversal begins at the head end. I always start in a single linked list at the head end. So I need to keep looking for the element in my list as long as two conditions hold true. Current can't become null, which would indicate that I've walked off the end of my list and I never did find it, or my index has become something greater than -1. Any index greater than -1 is a plausible, valid index in my list. So I'm going to create a loop here. While current is not null, protects me from walking off the end of the list, and index is still less than 0. As long as those conditions hold true, that indicates to me that I haven't found a node that I'm looking for yet. Inside my loop, we'll do a check. If the element in my current node, so I'm using my getElement method from the node class, if that current element equals, the element I'm looking for, then I found what I'm looking for. So I'm going to store in this index the current location where my current is. So I need one more piece of information. I need to keep track of where am I. I'll call it current index. So in the beginning, I'll start with current index equals 0 because the head node would have index 0. Which means every time I iterate through this loop, I need to advance current index along with advancing my current node. The way we move a current node is by setting it equal to the old current get next. That returns a reference to the next node in the chain. A couple of things to remember here. The equals method is used instead of the equals operator when comparing elements, because usually when someone is searching for something in a list, they're providing an object that looks like the one they're looking for. It isn't the exact same object in memory. They're searching for something based on its identifiable features. Think of a contact list in a phone. When you search for someone's phone number in a contact list, you know their name. You didn't already know their phone number, so you know some of the information. So the .equals method allows for comparing two elements for identifying information without requiring that they be the same object in memory. So it's important when we do object comparisons that we use the equals method instead of the equals operator. Something else to note here, if this confuses you, remember that assignment is always from right to left. So we are taking the current value of current, the old value of current, and calling its getNext method to return a reference to the node that comes after current. This entire right side, everything to the right of the equals sign, takes place before I make the assignment. So I'm returning the address of the next element, a reference to the next node, and I'm storing that reference back into my current. So everything on the right happens first, then I assign it to the left. So this is how I can advance my current node to the next node. So when this loop finishes, one of two things has happened to cause me to end the loop. Either I walked off the end of the list, current advanced to the point where current.getNext returned null, and I did not find the element I was looking for. The other possibility is that I did find the element that I'm looking for. If I never found the element that I'm looking for, this if condition was never true and index is still -1, just like I initialized it. So at the end, I return a -1, indicating that I never found the element I'm looking for. If I did find the element I'm looking for, then index became something greater than -1. And so I exited my loop because index was greater than -1, and that's the new index that I'm returning. So either way, whether I found it or I didn't find it, my loop has finished and I return that index. This way of navigating through a linked list using a node reference, some kind of cursor or a current reference, is going to be repeated in many, many of our methods. Anytime I need to start a traversal and search for something, I'm going to need some kind of traversal like this. Now we'll look at what it takes to insert an element into an existing list. And we'll start out with the user's perspective using the interface. So the user imagines that all it takes to insert an E after element B is to stick the E into the list after B, and the list automatically accommodates this. It makes room for element E, and E is simply in the sequence after B and before C. In order to do this using our nodes, we really don't have to do very much more than that. We begin by locating the node that contains our target element, in this case the node containing element B, because we want to add the E after the B. So we'll use a traversal very similar to what we saw in the indexOf method, where we'll begin at the beginning and we'll keep advancing our target node reference until we find the node whose getElement equals our target element. So here I've labeled target node. Target node is referring to the node that contains element B. Our second step then is to create the new node that contains the new element. This is the node we want to insert into our list. We need to update two next references, and it's very important that we do these in the correct order. We'll start by updating new node's next reference to point to the same node that's currently target node's next reference. Because we're inserting the new element E after the B, we need element C, or the node that goes with element C, to be the next node in the chain after the node that goes with E. So we'll update node E's next reference to point to the same node that is target node's next reference. After that, we'll update target node's next reference to point to our new node. And that's all it takes to insert the new node into our chain. So now after element B comes element E, and after element E comes element C. There's no shifting necessary. It doesn't matter how many nodes were in front of or after the E. Nothing had to shift. We did have to locate the target node, so there is an order n search at the beginning of this algorithm. But once we locate the target node, the insertion itself is a constant time operation. We do need to finish up by incrementing the size of our list. The code we'll need in order to implement the addAfter method is only slightly more complicated than what we saw in the previous slide. We still begin by locating the node containing the target element, but the interface specifies that if we don't find the target element in the list, we need to throw a no such element exception. Once we've found the target element, we can create a new node to contain our new element, connect the new node's next reference to the target node's next reference, and then connect the target node's next to the new node. One thing we need to account for is the possibility that we've added after the existing tail node. So if we determine that the existing tail node was the target node, we will update tail to refer now to our new node instead. And then we finish up by incrementing size. So here we are back in our single linked list code, and I've copied the steps from the previous slide. So we'll begin by attempting to locate the target node using a node traversal similar to what we've seen already. So I'll begin with a node reference that this time I'm going to call target node. And as always, we begin at the head end. I need to search as long as I haven't run out of nodes to look at and I haven't found the node that I'm looking for. So the only way that I'm going to know that I found the node I'm looking for is I need some kind of flag or something that can serve as a Boolean condition that I'll recognize tells me to quit. And I think for convenience sake, I'm going to use a Boolean value, found it. And right now I haven't found it, so I'll make it false. So my loop condition will include target node cannot be null. Target node being null tells me that I never did find this thing and I walked off the end of the list. But I also want to quit if found it becomes true. If I found this element, I want to stop searching. So as long as I have not found it, I'll continue searching. Inside, I need to determine if I've located the right target node. So if target node's element, target node.getElement dot equals the target element that I'm looking for, target, then I found it. Found it equals true. If I did not find it, then I need to move my target node to the next node. Target node equals target node dot get next. So I keep looking until either found it becomes true or target node becomes null. So when I finish this loop, one of those two things has happened, and I need to know if I didn't find it. So I fortunately have a Boolean value, found it, that will serve for this. So if I did not find it, I throw a new no such element exception. And this is the first time I've used that, so I need to import it from java.util. Something else I could use for a condition, if target node has become null, that would also tell me. Or target node is null. That would be another indication that I never did find the element. So if I get past all of that, it means I found it. Target node is pointing at the correct node. So here we need to create a new node to contain our element. This is the node we're going to insert. So I need a node of type T, and I'll call it new node. Equals a new node of type T containing my element. There's our new node. I need to set the new nodes next to the target nodes next. New node set next to target nodes get next. So I'm getting the next node reference from target node, and I'm using that as the same node that will be next for new node. And then I need target node, target node set next to new node. Those are the two connections that we needed in order to insert the new node in between target node and whatever comes after target node. There is the possibility that target node was the tail, which means the new node should be the new tail. And the way I can detect that is checking to see if target node is the same as tail. If those are the same reference, if they're aliases for one another, then I just added a new node after target node. So tail should be equal to the new node if target node was the tail. And finally, we'll increment our size variable. So those are the steps in our addAfter method. Removing an element from a single linked list can be a little trickier than adding. From the user's perspective, if they want to remove B, they just pluck the B out of the list, and the remaining elements collapse to fill the gap. There are never any gaps in the list. To remove a target element from our single linked list, however, we need to search not for the target node itself, but for the node before the target node. The reason for this is to cut the target node out of our list, we need to update its predecessor node's next reference to bypass the target node. So we're going to search for the node before the target node. We also need to remember to store the element that we're about to remove, because at the end of a remove method, we need to return the removed value. Once we lose our last reference to the target node, we would have no other way of getting that return value. So in order to bypass the target node, we'll update the predecessor's node's next reference to equal the target node's next reference. So we'll update the predecessor node setNext to equal target node's getNext. By doing that, there's no longer a reference in the list itself that points to that old target node, and so in effect it has vanished. So now all we need to do is decrement the size of the list and return the value that we stored. There are a couple of special cases that we need to be prepared for. In the event that the target element that we're removing is the head node, there is no predecessor node for the head node, so we need to treat that as a special case. We also need to account for the possibility that the node we're removing is the tail node, in which case predecessor node becomes the new tail. And finally, we also need to account for the possibility that there is only one node in the list and we're removing both the head and the tail node. In the code for the remove method that takes in a target element, we'll go ahead and handle a couple of those special cases first. We'll check to see if it's a single element list or if the target element is in the first node. We'll only do the search for the predecessor node in the event that it's not one of those special cases. So if we have located the node, we'll store a reference to the element being removed, we'll update the predecessor node's next reference to point to the target node's next reference, and we'll update the tail if necessary. We'll finish up by decrementing size and returning the removed element. We're back in our code now for the remove method, and I've included comments for a slightly enhanced set of steps from the previous slide. So first off, I'm going to handle a super special case that will simplify some of our condition checks later on. So first things first, we're going to check to see if this list is empty, and if so, we won't bother trying to locate anything. We'll just throw a no such element exception. So if this list is empty, we'll use our isEmpty method. We'll immediately throw a new no such element exception. Doing that because then I don't have to check for head being null. So if I get past that point, I know that I at least do have elements that I can start checking. So I'm going to start by checking to see if the element is in the head node. The reason this is a special case is that the head node does not have a predecessor node, so my general purpose search would be invalid. I would accidentally skip over the head node. So we're going to begin by checking to see if the head node's get element dot equals the target element I'm looking for, element. If that's the case, we need to remember the element. So I need a return value. I'm going to need a return value at the end. I'll use retval as the name of my variable. No matter what path I go through, I need the same variable. So I'm going to create a reference to a return value before I begin anything else. So it's going to be present throughout the rest of this method, and at the end, that's what I'm going to return. All right, so I've just located the target element in the head node. So retval equals head.getElement. That's the element I'm going to store, which was this comment right here. Just move my comment. All right. So I've stored that value. I need to update the head reference to bypass the this old head node. So here I need to update head. Head now equals head.getNext. So I'm removing the element that's at the first element in the list, which is stored in the head node. So head now bypasses that old first node and goes to the next node. Now, part 2 of that, there is the possibility that that was the only node. And if that's the case, then tail needs to be updated as well. If head just became null, because heads.getNext was null, I also need to update the tail reference. So if I find that head just became null, that indicates to me that I removed the one and only node out of this list. So tail also needs to be null. So that's our special case. Sort of 2 special cases. The element was in the head node, and it's possibly the only node in my list. By taking care of those right away, now we're free to implement our general case as an else. So if it wasn't the special case, it's our general case. This would be any target that isn't the first element. So we'll find our target node. And actually, we're going to find our predecessor to the target node. So this is going to be a node traversal similar to what we've seen before. It's just that we're going to be looking for our element in the next node from our current node. So here I'm going to create a cursor, or current. I'll call it pre-node. And we'll start at the head. We've already eliminated the possibility that the head node contains our element. That was our special case. So we'll begin at the head node. And what we're going to be looking for is, as long as the predecessor node's getNext is not null, we'll keep searching, because we're looking in the node that follows predecessor node. So once predecessor node's next becomes null, that tells us we've run out of nodes that contain our target element. We also need to know when to quit. So as we did in our add method, we'll create a Boolean flag for found_it. We'll know if we found the predecessor node. And until we find it, it's false. So predecessor node's next can't be null, and we can't have found it yet. Those will be the 2 conditions that cause us to stop searching. We'll check to see if we found it. So if predecessor node's getNext, remember that we're looking at the nodes that follow predecessor node. If the next node after predecessor node's element equals our element, we found it. Found it equals true. All right, let's unravel that. That's a big sequence. We're trying to find the node in front of the node that contains our element. So predecessor node's next is the node that we're considering to be the target node. It's under consideration. So we'll get the element of that node and see if it equals the element we're looking for. So that big long chain looks in the next node, checks its element to see if it equals the element we're looking for. So if we find the node whose next element is equal to our element, we found it. And that breaks us out of our loop. If not, we move our predecessor node to whatever comes next. Predecessor node.getNext. So at the end of this loop, we either ran out of nodes that could possibly hold our target node, our target element, or we found it. So as before, if we did not find it, if not found it, we'll throw a new no such element exception. All right, if we got past that point, if we got past throwing a no such element exception, we did find the target node. So before we remove the target node, we better store retval equals the value in our pre-node getNext get element. That's the element we're about to remove from this list. So now we have our 2 steps or 1 step, to bypass the target node. So pre-node's next should no longer point at whatever it was pointing at, the target node. Now it should be set to pre-node getNext. So we're going to move 2 steps past the node that was next. So pre-node set next to the target node's next. Pre-node getNext is the target node. Pre-node's getNext is the node that comes after the target node. So that's what our predecessor node's next is now pointing to. We've just cut the target node out of the list. We do need to check to see if the node that we removed was the tail node. So a way that we could detect that, if pre-node's getNext is null, we know we just removed the old tail node, in which case predecessor node is now the last node in this list. So tail is equal to the predecessor node. Finally, so let me close this. That was our general case. No matter how we removed something, whether it was the head node, the only node, or the general case, we need to decrement size and finally return that return value. While we aren't going through the implementations of all of the remaining methods, you can use the techniques that we've seen so far for node traversal, for adding new elements, and for removing existing elements to the remaining add and remove methods. You can also apply these node traversal concepts in our indexed methods by starting at the beginning of the list and counting the number of nodes that you've traversed in order to find a given index location.